Okay, so good evening, all of you. So today we are going to discuss about the week 2 session. So the class is of about Introductory Organic Chemistry Part 1, which is an NPTEL platform course, and you will find all the videos of this course available on NPTEL. So the course instructors are Professor Harinath Chakrapani and Professor Niraja Dashaputre. These are from ICER Pune, and I am your PMR Teaching Assistant Simran. So we are going to discuss about this nomenclature and conformations in this week 2 session. Okay. So guys, I hope you have gone through my video which I have uploaded last week on week 1. So anyone has any question regarding that video, please let me know so that I can answer your questions. So anyone has doubt regarding the week 1 video, the lecture which I have taken? Yes.
Ma'am, that this antibonding theory is there, no antibonding orbitals one. So
Yes,
can you
yes.
please once in just quick review, can you go through that one antibonding orbitals?
Okay, so how it is going to form, right? You want to know that?
Yes, yes.
Okay. So see what happens when you have molecular orbitals, right? Molecular orbital in the sense that two hydrogen molecule, if they are interacting, right? H2 is forming, so two molecule of hydrogens are interacting. So the molecular orbital of two hydrogens, basically two hydrogen atoms, combine, overlap with each other to give two type of bonding orbitals. One is anti-bonding and one is bonding orbital. How it is going to form? See, the molecular orbital of hydrogen atoms overlap with each other. So if the overlap is constructive, like overlapping is happening where the two poles are same, then the constructive overlapping is taking place, right? So it will give you the rise of bonding orbital. Whereas if the overlapping is such that two orbitals are uh, overlapping in a destructive manner, the two poles are not equivalent, so here anti-bonding orbitals are getting formed. So the constructive overlapping between the molecular orbitals will give you bonding orbitals, whereas the destructive overlapping between the molecular orbitals will give rise to anti-bonding orbitals, right? So these are the molecular orbitals, atomic orbitals, which is generated from molecular orbital overlappings. So that based on the constructive and destructive overlapping, you will have two orbital, antibonding and bonding orbital for each of the cases. So is it clear now?
Yeah, okay, ma'am. I think I should go through the books for that more reference.
Yeah, you can go through that book so that you can get how this destructive and constructive overlapping is taking place. So that you have to look into the books.
Okay,
Okay.
thank you. Thank you.
Okay. Thank you so much. Any other questions other than this? Okay. If there is no question, so can we start with week 2 lecture? Okay. Guys, please join on time. Okay. So in week 1, we have learned about the molecular orbital theory and how it is important in constructing the orbitals, right? So in week 2, we will be discussing about the nomenclatures and the conformation of cyclohexane, basically the cycloalkanes. Okay, so here you will get to know how the conformations are present in cycloalkanes, and also how you can nomenclature them according to the basically we will learn about the bicyclic system, how the nomenclature is occurring in the bicyclic fuse systems, right? So coming to the problem number 1, so here they are asking which of A to D is the most unstable conformation. So here in the first part you can see there are two type of conformations. First of all, first is staggered conformation and second is the eclipsed conformation. So the staggered conformation, as you can see, is this kind of conformation. When you draw the Newman projection, the staggered conformation is this, and the eclipsed conformation in the Newman projection is this, right? So how, first of all, you need to know what is this staggered and eclipsed conformation and how the dihedral angle plays an important role here, and also the strain which comprises in both the conformations, right? So here we will be talking about the eclipsed conformation here. See, when you draw the Newman projection for the eclipsed conformation, this is the dihedral angle between the two hydrogen that is present here. I'm talking about this molecule only right now. So here the two hydrogens are eclipsed. It is having a dihedral angle that is 0 degree. There is no angle between the two hydrogen, they are overlapping, right? So here, when they are overlapping with each other, there is a strain which is developing in between these two hydrogens that are known as torsional strain. Okay, based on a dihedral angle, we can say that here the torsional strain is present. But now, when we come to the staggered conformation, this conformation, here the angle between the dihedral angle between the two hydrogens now is 60 degree. So when you have this 60 degree dihedral angle, the torsional strain is although released, but here what you can see is the steric strain only. Whereas in this eclipse conformation, there is torsional strain as well as steric strain which is present. Steric is not important here because here two hydrogens are there which are not that much bulky, right? So that's why we are not focusing on that steric strain here, but torsional strain is although present here. So when we are talking about the staggered conformation, the two hydrogens are at 60 degree angle to each other. So now torsional strain is relaxed. The two hydrogen are not overlapping, but what happens here is steric strain is there. But we can say that this conformation, that is a staggered conformation, is way more stable than the eclipse conformation. Is this much clear to all of you? Why staggered and why staggered conformation is more stable than eclipsed? Is it clear? This much.
Clear.
Okay. So here we are discussing in the question that which of the following is most unstable conformation. So here you can see, as you can see, two staggered conformations are here and two eclipsed conformation are there, right? So you can easily detect that out of these four, two staggered conformations are although stable than this two eclipsed conformation, right? So these conformation, these two AB are in turn is more stable than these two conformations. So now we have to talk about only C and D. We have to worry about C and D, which is most unstable, right? Because here these two are staggered, so which in turn is more stable than this eclipsed conformation. So now we have to worry about these two eclipse conformations. So in turn, in which of the following is more unstable? So you have to find that only. So now, as you can see here, you have to see two type of strains. First is torsional strain and second is steric strain. So now here torsional strain is present in all in these two very much, right? But here you have to worry about the steric strain. So now Cl is in surrounding of this hydrogen. So chlorine is bigger than hydrogen, but here, as you can see in this D part, chlorine is in close proximity with this chlorine, another chlorine. So the two of them are bulky enough, right? So now the steric strain which is present between chlorine and hydrogen, bromine and hydrogen, is not that much which is present in between chlorine and chlorine molecule, right? So here steric strain between the Cl and Cl atom is very much, so that is why it is contributing highly towards the instability of this molecule. Because of the steric strain which is present in the D conformation, it is much more unstable than C. Is it clear to all of you why D is more unstable? Because here, first, what happens? Chlorine is present in close proximity with this hydrogen, Bromine is facing the steric repulsion because of this hydrogen, and again, chlorine is facing the repulsion between this hydrogen. But in this case, the two chlorine are present in proximity, and the steric strain is arising because of the higher sterically bulky ClCl atoms, right? So, any doubt up to here why this D is more unstable than C? All of you have understand what I'm talking about. So just tell me the correct answer. Which would be the correct answer among the four?
D is the correct answer.
Yeah, D is the correct answer. Why? Because in between of C and D, the steric strain is present higher in this ClCl atom. That is why, which is corresponding to the instability of this conformation. Whereas in this, we have an halogen which is present in the close proximity of hydrogen, which is not way bulky than chlorine. Okay, so that is why we are getting option D as a right answer. So all of you have understood. Any questions about this question? Any query? Okay, should I move to problem number 2 then?
Okay, ma'am.
Okay. Please answer, guys, okay? So that I'll get to know that you are here. Okay. So, in the problem number 2, they are asking which is the most stable structure of one isopropyl 4-methyl cyclohexane. So you have to identify the most stable structure of this one isopropyl 4-methyl cyclohexane. So as you can see, there are four options in which axial and equatorial positions are different for this methyl and isopropyl group. So you have to tell that which is more stable. So any guesses around which is the more stable conformation in between these four?
B. Yeah, the
Sorry,
B.
B. So any other answer other than B? Someone is saying A, na? Okay. See, what they are asking the most stable conformation. And first of all, you need to know the A values of this methyl and isopropyl group. What you mean by A values? The basically it is the value which which informs you that the preference of this particular group towards the equatorial position. So, how much preference it has to be in equatorial position, this is reflected in the A values, right? So now, as we can see here, the A values which is present here, see, A values of this particular delta G preference for equatorial for methyl is 7.2, whereas the isopropyl group, the presence for the equatorial position is 9. So you can see that it is a bulky group than methyl group. So that is why it prefers to be in axial position than the methyl. So I'm not saying that methyl is not favoring the equatorial position, but if you compare between the two, then you will find that as you are going down in the table, the bulkiness of these particular groups are increasing. So that is why their preference to be in the equatorial position is increasing. So whenever you have a choice, in this case there is no choice. The stereochemistry is not mentioned, so you guys are treating both the substituent at the equatorial position. But if you have any choice to put one at axial and one at equatorial, so methyl will be at axial and the isopropyl group will be at equatorial because of the bulkiness of the group. Is it understood to everyone why I'm telling this? In this case, there is no stereochemistry mentions. That is why you are placing both the substituent on equatorial, which is the very preferred conformation. But if you have any of the restriction to put one group at axial and one at equatorial, so you will prefer isopropyl group to be at equatorial position rather than the methyl, because the isopropyl group has more bulkiness than methyl group. Is it understood to everyone? Okay. So,
Yes, ma'am.
so here the correct answer would be option number B, because here they are asking the most stable structure for this one isopropyl 4-methyl cyclohexane, and it will prefer to be at equatorial position for both the substituents, because here if these groups are present at axial position here, as if this methyl is present at axial position, the hydrogen which is present here and the hydrogen which is present here, so this methyl will face a 1,3 diaxial interaction because of these hydrogen. That is why this methyl will place towards the equatorial rather than the axial position. So similar case with this, it is also facing, if it is at axial position, it is also facing the 1,3 diaxial interaction. So to get rid of the 1,3 diaxial interaction, these substituent will prefer to be at equatorial position rather than the axial position. Okay. Okay, so here the correct answer will be option number B. Fine. So, any doubts regarding this? I hope there is no doubt. It is a very simple question. Okay, so I'm assuming that there is no doubt. So, I'm going to problem number 3. So, in problem number 3, they are asking which structure is different from the following. So, can anyone tell me which structure is different from the following? In this case, particularly, what you have to look is that here the two
B.
chlorine, sorry, which structure?
A. A.
No. Here, what you have to look is, just forget about the stereochemistry ones and just tell me that one chlorine is present at above the plane and two chlorine are present at below the plane. Okay. So in option number A, two chlorine having the same stereochemistry and one chlorine is having another stereochemistry. Similarly, in option B, it is the same as it is written at here, but rotated. But in option C, as you can see, the two chlorine are below the plane and one chlorine is present at above the plane, which is present here also. Two chlorine having the same positions and one chlorine is different from each other. The relationship is same as well, 1, 2, 3, 4, 5. As you can see, 1, 2, 3, 4, and 5. So in option number D, it is the only option you can see all the three chlorines are present below the plane. So which is not same as in the case of this structure. So which will be the correct answer now?
I think D.
Yeah. Because yeah, D is the correct answer. Why? Because here what you have to see is according to the question you have to proceed, right? So see first of all, see the options which are available to you. Here they are asking the different structure than this. So you can see in option A, two chlorine are present on the same phase, whereas other chlorine is opposite to that phase. In the structure also, two chlorine having the same stereochemistry while the other chlorine has other stereochemistry. Here also B is the same as the structure is given, and in option C, the two chlorine having the same stereochemistry but other one third chlorine is having another stereochemistry. It is the only option D in which all the three chlorine having the same stereochemistry, which is not as the structure which we have mentioned, right? So here the option D is correct because this is the only option which is having a structure different from which is what is given here, right? So option number D will be the correct answer. So any questions regarding this particular problem? Any questions, guys? Okay. So I'm moving towards the problem number 4. So, guys, it is a very simple questions. I have just put it this question so that all of you can understand. It is the basic of nomenclature, IUPAC. So they are asking select the correct IUPAC name for the following compound. So, can anyone tell me the correct answer very quickly?
A. A is the correct answer.
A is the correct answer. Anyone else?
C.
C is the correct answer.
C.
Okay. Any
A is the correct answer, ma'am.
A is the correct answer.
A
Any
is
other?
correct answer, ma'am.
Okay. We have two options, A and C. So, how many of you are saying A? Okay. Okay. C. So, just look into it. So, at least you guys has responded. Good. Okay. So first of all, according to IUPAC, first of all, what you have to see is the preference which you have to give for both the substituent that is present at this position, right? So here, according to IUPAC, what is the rule that the higher atomic number, first of all, the higher atomic number will get a higher preference. So as you can see, that bromine has a higher atomic number. Guys, please do not join. Why you people are so late? Okay. So according to IUPAC, the rule is first of all atomic number you have to see. So higher atomic number will get higher preference. So here Br will get higher preference than chlorine. So you have to numbering it according to 1, 2, 3, and 4. Fine with everyone up to here? Fine. So according to this, you have to name it. So here, first of all, another rule of IPAC is
If we start numbering from bromine from right hand side, then methyl will come at 3 position. But if we start numbering from left hand position, then methyl will come at 2 position.
Yeah.
So lower substituent and lower carbon is more preferable, na?
Okay, so okay. I got your thing. See what happens here is, first of all, you have to see the preference which is present at the substituents at the end of the chain. Okay, these substituent present at the end of the chain. You are saying the right thing, but see, if you are talking about this Br, the atomic number for Br is higher and atomic mass for Br is higher, right? So you will have to number it 1 and then you have to go for the particular chain. See what you have to see here is the substituent which is present at the end of the chain. That is according to that you have to number it. The rule 2 comes into play which you are talking about, but rule number 1 is that only. And also if
No, ma'am. I think at the time of writing, we will write first according to the alphabetical order.
Yeah, alphabetical
But
order.
I think numbering should be from left hand side.
Numbering should be.
You please check.
Okay, okay. I'll check for that also. I will let you know. Okay, I have to also check for that. What you
Okay,
are
sure.
thinking. Yeah. So option number A and C. In these two options, we are confused, right? See, according to me, first of all, you have to number that particular atom which having the higher atomic number, and the substituent which is present at the end, you have to number that only. So I will check this question and let get back to you guys. Okay. So we are going to problem number 5 instead of that. So problem number 5, guys, here.
I think in the previous
Yeah.
problem, both option A and C are correct.
Yeah. Actually, it could be, but the thing is, what she is claiming is also right. Both A and C are debatable, but we have to check the IUPAC nomenclature. I cannot say her that she is not correct. She is also correct because the two substituents are also coming on to. If we are naming from this chlorine, the lower number is getting at
Actually,
the.
there is no measure of violence in the room.
Sorry.
Actually, actually there is nothing violence
measure balance okay. So that is what I'm claiming, that according to me, option A is correct. But if you guys have option number C in mind, then also I will have to check, and also you people also check. Okay. So that's why I'm not saying that she is wrong, because I haven't actually checked. Okay, I will get back to you guys according to this problem number 4. So we are skipping this part right now. Okay. So coming to the problem number 5. Anyone has to say something? Okay. Can you please mute your mic if you don't want to say something? Mahima, can you please mute your mic? Thank you. Okay, so coming to the problem number 5, identify the correct representation of the ring flip for the following compound. So there is a thing which is known as ring flipping in the cyclohexanes. So what happens in the ring flip is, first of all, there is a rapid equilibrium which is happening in this cyclohexane ring. They will flip from this conformation to this conformation. So how it is going to happen? When you rotate, when you mark this carbon as one and at this carbon, when you rotate this carbon in this fashion, this kind of conformation you will get, right? If you are rotating this and this, you will get a flipped conformation of this particular cyclohexane ring. So what happens here is the substituent which is present at this ring is now, if it is axial in this ring, it is now coming equatorial in the flipped conformation, right? This is the whole concept between this ring flipping. So it is a rapid equilibrium which is occurring between the cyclohexane rings, because all of you know that the cyclohexane rings have lot more conformation than chair conformation. These are like, first of all, this chair conformation is going to half boat, then the twist boat conformation boat, and again the half chair conformation is getting formed, and then this ring flipped chair conformation is getting formed. So this is how it travels through an energy barrier, and also these are the all the conformation which are shown by a cyclohexane molecule, right? So as you can see that basically this chair conformation is the one conformation which is more stable for the cyclohexane molecule, and the both then this half chair is the least stable conformation for this cyclohexane molecule, right? So these are the conformations through which it is going from A to another A ring, but flipped. Okay, so this is how there is a rapid equilibrium which is going from this particular chair conformation to this ring flip chair conformation according to this energy barrier diagram. So here they are asking, identify the correct representation of the ring flip for the following compound. So here, as you can see, there is a ring flip which is occurring into this molecule. So now the ring will move towards this. So all the four options, you can see that the ring is flipped. But now what you have to see, now the substituents on present on this particular ring, how they are coming into this ring flipped. Okay, so here all the flipping is correct, but the substituents are playing role. So as I have told you earlier that here when the ring flipping is taking place, the substituent which is present on initially on the ring, if it is axial, then it is going to the equatorial position in the flipped ring. As you can see here, this axial hydrogen is this hydrogen is axial in this particular conformation. When the ring flipping is taking place, this hydrogen is getting as an equatorial position, as you can see here. This hydrogen which is present at equatorial now is present axial in this flipped conformation. Is it clear to everyone how this flipping is going? Rapid equilibrium is there in between these flip structures, and how these conformations are playing role in achieving this one chair conformation and another flip conformation. Is it clear to everyone this much? Just leave the question aside. I'm talking about the ring flipping only. The ring flipping is happening between the cyclohexane ring, and there is a rapid equilibrium which is occurring between the cyclohexane ring. So the conformation which are present in one ring flip is these. First of all, this first the chair conformation goes to the half chair conformation. Then the half chair conformation went to the twist boat. Then the boat conformation is achieved, and then again the twist conformation is there, and then the half chair conformation is again achieving, and then this flipped ring you can see is forming here. So this is what the several events which are involved in going from A to A. Is it clear to everyone how this ring flipping is taking place? Any doubts, guys, please?
No, ma'am.
Okay. So please respond so that I can know that you guys are getting my theory. Okay. So if there is no questions, so what in the question asking is that write the correct representation of the ring flip. So you have to worry about the substituent which are present on this flipped ring. So flipping is there in all the four options, but substituents are going in another way. So here, if this methyl is present at the axial position in this particular conformation, in the ring flip conformation, it should be at equatorial position, right? As we have seen here, after flipping, this axial hydrogen is going to this equatorial, and this equatorial hydrogen is going to this axial hydrogen. So ring flipping occurs, and these substituent will go from axial to equatorial. Anyone has any question? Guys, please, if you have any question only then please put your mics on. Otherwise, please mute them. Okay. Okay, here what I was talking about is this methyl is present at the axial position, so at the ring flipping it will be at equatorial position. This fluorine which is present at the equatorial position, it will go to axial position in the ring flipped conformation. And this also it is present at the axial position, it will be going to equatorial position. Fine. So if you start the numbering from anywhere, let me start the numbering from this one. Let me number it according to this. One,
Option A, ma'am.
option A. Okay. Option A. Yeah. Any other option you can see which could be correct? See, you guys are thinking according to the preferences.
Option A.
Yeah, option A. Option A is the correct answer. How? First of all, you need to number this particular ring, and if you are rotating this ring according to this here, then you will get this particular conformation, right? So what happens here is, if the axial methyl is present here, then it will go to the equatorial position, and when you number it 1 2 3, this is in the relation of 1 2 3. Now this fluorine which is present equatorial will go to at axial, and this axial ethyl group will go at equatorial position. So that is why the substituents are flipping with the ring. So here the correct answer should be A, because all the groups are now flipped according to the ring flip. Fine. Is it clear to all of you why these substituents are in this flipping manner? All of you understood the concept of ring flip?
Yes, ma'am.
Okay. Any doubts, please ask me.
No, ma'am.
So, going to the problem number 6. So, it is a very straightforward question. So, again, they are asking in Gauss conformation, the methyl groups are. Basically, we are talking about the conformation which is Gauss. Gauss means if you have this system for methyl, if it is a butane system, I'm talking about. If this is CH3 and also this is CH3, the behind carbon is also CH3. If it assumes this, if it is a butane system. So here, the Gauss conformation is the conformation in which both the methyls are present at 60 degree to each other. Gauss conformation is although a staggered conformation, but here methyls are present at 60 degree to each other. So this is known as the Gauss conformation. So what they are asking is, in the Gauss conformation, the methyl groups are present at what dihedral angle? So according to this staggered conformation, you can say the angle between them is 60 degrees. Yeah, 60 degree. So here in the Gauss conformation, the two methyl groups have the dihedral angle 60 degree. So the option number A would be the right answer. So in Gauss conformation, the two methyl groups are present at 60 degree apart. Fine. Any doubts?
No, no.
So now again on the Gauss conformation. So they're asking the Gauss conformation is less stable due to. See, what I have told you here is you have to see two interactions. That is, first is torsional strain and second is the steric interaction, right? So here in this eclipsed form, you can see that two methyl having torsional strain as well as the steric strain. But when you go to this Gauss conformation, what happens? The torsional strain is also released, but here the two methyl groups are facing towards each other. So there is a steric repulsion which is occurring between the methyls. I have told you, if you are talking about ethane, where hydrogens are present at this position, there is no steric. The steric repulsion is quite nearly zero, because hydrogens are very small, so they will not impart steric hindrance. The only strain which is present there is the torsional strain. But when you have methyl, when you have a butane system instead of the ethane system, if you draw the Newman projection, you will find that in the eclipsed conformation, the two methyls are facing towards each other, that the angle is 0 degree in the eclipsed conformation, so they have torsional as well as a steric strain. But when you are moving the methyl groups 60 degree apart from each other, the torsional strain is also getting relaxed, but the steric strain is still there. So here methyl groups having the bulkiness and facing each other. So here you can say the strain which is present here is the steric strain. So the steric strain is the only strain which is present and giving the instability to this particular configuration. Is it clear to everyone why this conformation is having which strain is responsible for the instability of this conformation?
Yes.
Okay. So which will be the correct answer now?
Torsional strength.
Torsional, it's not the torsional strain. See, torsional strain, what I have told you is, it is present in the eclipsed conformation. But
But
when you,
ma'am, when
yeah,
compared to anti, there will be some torsional strain in case of Gauss, no?
there is still some torsional strain, but it is not contributing towards the instability of this particular conformation. If you are talking about the eclipsed conformation, then the majorly the torsional strain is there. That is why the instability is there. But when you are talking about a staggered conformation and although specifically about a Gauss conformation, the torsional strain is also relaxed because of the dihedral angle which is getting increased from 0 degree to 60 degree. And but here the methyl groups are bulky, that is why the steric strain is competing. So here the steric strain is the only reason why these molecule having the instability. If you are talking about the anti, which I am also coming in the a few slides, if you are talking about the anti conformation now, the anti conformation doesn't have any strain. See, the torsional strain is also relaxed, the steric strain is also relaxed. because methyl groups are now anti towards each other. They have the dihedral angle of 180 degree, right? So here, in the anti conformation, there will be no strain. So that will be the maximum stable conformation. So here the main strain which is responsible for the instability of this conformation, that is the Gauss conformation, is the steric strain only, because torsional is also relaxed because of the dihedral angle increase. Is it understand to you, or have
Yes,
to
yes,
repeat?
ma'am.
Okay, okay. So in the options, which will be the correct one? Anyone? Is a hydrogen bonding? No, hydrogen bonding is not there.
Van der Waals repulsion.
Yeah, van der Waal repulsion. So van der Waal repulsion will be the correct answer. You can tell the steric hindrance, van der Waal repulsion. There is a repulsion between these methyl groups. That is why the cos conformation is less stable than the eclipsed or any other conformation, right? So is it understood to all of you? You can see also this kind of thing here. If the eclipsing things are there, there is torsional strain which is playing the maximum role, right? But when you have this methyl eclipsing now, only then steric repulsion will come into play. And if you have Gauss interaction, only the steric strain is there, because torsional is relaxed because of increase in the dihedral angle. Torsional is when the dihedral angle is 0 degree or the eclipsed conformation is there. You can also say the eclipsing interaction, the torsional strain. Okay, so this is how this table can give you a idea of how the strains are there in the eclipsing and staggered or Gauss conformation. Okay, clear to everyone? Okay.
Yeah.
Yeah. So coming to the problem number 8. So I have already answered this question because of your question. So they are asking which of the following is least stable. So which is
Cos
least stable?
confirmation.
Yeah. Which is least
Eclipse
stable?
confirmation. Eclipsed
Yeah,
confirmation.
eclipsed conformation. And which is more stable?
Anti.
Yeah.
Staggered. Anti.
Yeah, staggered is, although see what happens, staggered and eclipsed are the two conformation. Staggered is although much stable than the eclipse conformation, but in staggered conformation there are two conformation, that is anti and Gauss. So in anti conformation is more stable. I hope I have, yes, I have this slide, so you can see, you can relate this here. This is eclipsed conformation, this is eclipsed conformation. Staggered conformation is the these two, but in the staggered conformation, there are two conformation, that is Gauss and anti. So in these, you can see the methyl group is present in at the 60 degree to each other. So there is steric strain in the Gauss conformation. But when you come to this anti conformation, as the dihedral angle between the methyl groups are now 180 degree, so torsional strain is also relaxed, steric strain is also not there. So that is why anti conformation is the most stable conformation. Okay, is it clear?
Ma'am.
Okay. So
Yeah.
the least stable conformation will be eclipse conformation. See, I have purposely added this slide. So if you are talking about this dihydroxy alcohols, see, so what you can say, uh, uh, if I tell you that which is the most stable conformation between Gauss and NT. So now, can anyone tell me which is the stable conformation between Gauss and NT?
Gotcha. Due to hydrogen bonding.
Yeah, due to hydrogen bonding. So you have to have an idea what are the substituent that are located in the Gauss and NT conformations. Is there is any other bonding which is responsible for the stability? Here the hydrogen bonding is playing role. So that is why Gauss conformation is although more stable in this case than the NT conformation. So the linear concept is this, but if you have two hydroxy groups that are present to 60 degree to each other at the Gauss conformation, now they will show a hydrogen bonding, and now this hydrogen bonding will give more stability to this particular conformation. So now anti conformation is become it is become less stable than the Gauss conformation, right? So this is how you have to think about it. Is it understood to all of
So
you?
any.
Yeah.
Ma'am, any substituent which is able to form the hydrogen bonds, if they are in Gauss conformations, then they are more stable than the anti.
Yeah, you can say that. Depending on the substituent, I will say if how they will affect the hydrogen bonding, how strong the hydrogen bonding is. You can say that yes, Gauss conformation is more stable than anti. Okay. So basically,
Okay.
hydrogen bonded groups are preferred Gauss conformation because of the hydrogen bonding which are there in between. Okay, they prefer to be in Gauss conformation. So any other question? So okay, so I am thinking that all of you have understood. So coming to the problem number 9, because we have to now run. Okay. So problem number 9 is which of the following best explains the reason for the relative stability of the conformer shown. So see, it is also related to what I have told you. So anyone can answer this. Which of the following best explain the reason for the relative stability of the two conformer? So the first option is the first has more torsional strain. Second option is first has more steric strain. The third option is second has more torsional strain. And the fourth option is second has more steric strain. So which is the correct answer? Anyone?
D, D,
Which is the correct answer?
D.
Yeah, D. Any other answer than D? So all of you are thinking on the same line. Okay. So there is no other.
Two has more static strain.
2 has more steric strain. Yeah. So option number D, right? So here what you have to see is here first has more torsional strain. No, because torsional strain is not present, right? Because here the dihedral angle is 60 degree. It is relaxed. If you go to the second option, that is first has more steric strain, although here methyl is present at 60 degree conformation to this hydrogen. Hydrogen being smaller in size, so it is not giving the steric strain in this particular conformation. Whereas when you go to the second molecule, it has, if it has more steric strain, so you can say the steric strain is relaxed because the dihedral angle is now 60 degree. But here is steric strain which is present, as I have told you that two methyl group are repelling each other, so they have the steric strain because of the bulkiness of methyl group then hydrogen. Okay, so the option number D will be the right answer. Clear to everyone?
Yes, ma'am.
Okay. So coming to the problem number 10. So they are asking among the butane conformer which occur at the energy minima on a graph of potential energy versus dihedral angle. So they are asking if you are talking about the butane conformer, all the conformer of butane. So which is the conformer which is coming at the energy minima, which is the most stable conformer amongst all the conformer of butane. So can anyone answer this?
Anti.
Anti. Any other answer? See, they are saying which occur at energy minima on a graph of potential energy. So, energy minima. So, they are asking either it is a gauche conformation, eclipsed or totally eclipsed conformation, gauche and anti conformation, eclipsed or anti only. So, this is the energy profile of this particular conformer of this butane. So, they are asking about the energy minimas. Fine. So these are the energy minimas, right? 180 is although A only. Okay, this is A. So what happens here is, first of all, if you are going towards this 0 degree, that is the eclipse conformation, to this 60 degree, a Gauche conformation is achieved. Now this is the stable structure from this eclipse conformation, so it achieves a minima. Then it goes to a higher energy because of the eclipsed conformation. again, which is achieving because of the another dihedral angle of 60 degree, that is 120 in total. Okay, so now it is also going to a 60-degree rotation at this 180 degree. So here the conformation which lies is NT. So the minima which is occurring here in this graphs is this particular two and this particular two, the four I have mentioned, right? So now they are asking in the question which occur at the energy minima on a graph of potential energy versus dihedral angle. So which of the conformation is arising at the energy minima? Is it the NT only?
Gauss, Gauss and anti.
Yeah. So you have to see, according to the question, you have to answer which occur at the energy minima. Because the Gauss conformation is also stable conformation, stable enough from this eclipse or the totally eclipse conformation. So you have to mention that yes, energy minima is present at Gauss and anti, both of them, right? Not NT alone. NT is the least energy conformation, but at energy minima, you have to see how the graph is going, how the trend is. So you can basically see that when you are increasing the dihedral angle by 60 degree, after every 60-degree rotation, you will get another set of conformers, right? So you have to see which is having a higher energy, which is having a lower energy. So at the minima, you will see that only Gauss and anti conformations are there, because eclipsed and totally eclipsed conformations having the higher energy than these conformations. So the correct answer will be Gauss and anti conformer, which is occurring at the energy minima of the graph. This is the energy minima. Fine. These for the energy minima. Any questions? Any doubt regarding this question?
No, ma'am.
Okay, so all of you have understood this. Okay. So coming to problem number 11 now. So they are saying identify the most stable conformer. So according to this particular stereochemistry, now you have to identify the most stable conformer. So now you have to put these substituent according to the stereochemistry. Now you cannot randomly place all of them at equatorial. You have to stick to the stereochemistry and then you have to place the all the groups at equatorial direction. So can anyone tell me which is the correct answer? Keeping the stereochemistry in mind, please answer. Okay. Just draw these things and then you will get to know which is the correct answer.
Is it A?
A. Okay. Anyone else? Any other answer? Then A. So all of you are agreed with A.
Yes, ma'am.
Okay. So see what they are asking here is the most stable conformation. So now if you place this methyl as 1, put this as 2, this as 4, right? So you can see, people are joining. Okay. So if you number it 1, 2, 3, and 4, then you will see that at 1, the methyl group is at below the plane. So here in this conformation, the methyl group is below the plane. When you come to second carbon, now the second carbon, methyl, is above the plane. It is coming at above the plane. So now at the fourth position, the methyl is also above the plane. So in this conformation, this is above the plane. So all the three methyls are setted according to the stereochemistry, and also the 3 methyl are present at equatorial position. So I have told you the preference for methyl group uh, at this equatorial position is because of the 1,3 dioxane interaction which is facing them when they are present at the axial position. So that is why here the stereochemistry is also fulfilled, and also the 3 methyl groups are getting at the equatorial position. So this is the most stable conformer. Although if you go to this second option, then here you can see that the stereochemistry is not matching at the fourth carbon. Here they are saying that methyl is above the plane, but here the methyl is coming at below the plane. So stereochemistry is not matching. When you go to this particular conformation 1, 2, and 4, so here also you can see that one is below the plane, second is above the plane, and fourth is also above the plane. Stereochemistry is matching here, but what you can see is it matching here, guys?
Steric strain will be there
Yeah,
somewhat.
yeah. What you have to see here, that the steric strain between these two methyls are also there, na? This is also at the equatorial position 3 methyl, stereochemistry is matching, but C is not the correct answer because the two methyls are coming at the close proximity. So here the steric strain is present between these two methyl groups. So that is why C is not the correct answer, although the stereochemistry is matching, although the three methyls are present at the equatorial position. There is a competition between A and C. So here in the C option, two methyl groups are coming together towards each other, and the steric strain is there. Whereas in A option, there is no steric strain. So that is why A is more stable than option number C. So the correct answer will be option number A. So anyone has any problem in this question? Guys, please speak up. I will say that please practice these problems by writing the cyclohexane, by placing the different substituents on the cyclohexane ring, so that you can know that what you have to see is the stability in terms of torsional, steric strain, and also you have to have the stereochemistry settled. Okay, any questions? Should I go to the problem number 12?
Yes, ma'am.
Okay. So coming to the problem number 12. So in this, they are saying identify the compound with the highest ring strain. So the options are cyclomethane, cyclopropane, cyclobutane, and cyclopentane.
Cyclopropane.
Propane.
Cyclopropane.
Cyclopropane. Any other answer? Anyone feels that cyclopropane is not the correct answer, or any other option is the correct one? So why cyclopropane is more stable, having the highest ring strain?
It is trapped. It cannot move.
Yeah,
Its bond angle is 60 degree, which is way far away, less than the 109.5.
yeah, 109.5. Butane is also packed. It cannot have other conformation, right? So if you talk about pentane, it can go, but butane cannot go beyond that particular structure. So here what you have to see is the dihedral angle. So basically the angle between cyclopropane is 60 degree, and in butane there is 90 degree, and in cyclopentane there is 108 degree angle, and in the cyclohexane ring 120 degree angle is there. So the bond angle which is present in the sp3 carbon should be ideally at 109.5 degree, right? But here when you go from this particular conformation for cyclopropane, the 60 degree angle is way smaller than the 109 degree angle. So here the ring strain is getting very much, and the strain is also because of the another thing. Can anyone tell me another reason of the steric strain between this cyclopropane ring? This is the correct reason that the dihedral angle is way less than 109, which it should be. But another aspect of that, can anyone tell me?
Torsional strain.
Yeah, torsional strain. Very good. So here, torsional strain is also present, guys. What happens here is, if you are talking about the conformation, you have to stick to steric and torsional strain. So here, between these hydrogen, if you place these hydrogens, then you will see that there are torsional strain between these hydrogens. So these hydrogens are eclipsing towards each other. So these are eclipsing. So there are three eclipsing interaction which is happening here. So here, the eclipsing interaction is also governing for the highest ring strain. So that is why you can say the torsional strain as well as the lesser bond angle. Both of them compile together to get you the highest ring strain in the cyclopropane moiety. Is it understood to everyone?
Yes, ma'am.
And which is the theory which is giving these kind of explanation? What is the name of that theory? Anyone remembers? Which is the theory which is giving the particular bond angle reason in the text. You have seen that sp3 carbon having the 109-degree angle, and cyclopropane butane having the very lesser angle than that, so that is why they are strained. But there is a theory which is giving that explanation basically. The name of the theory is, anyone? Guys, you must know this. You are actually knowing it because you know the concept. So this is the Bayer strain theory, right? Bayer strain theory is the theory which is giving you the ring strain in the particular cycloalkanes. It is the famous theory in which they are claiming that sp3 carbons having the bond angle 109-degree, and if you have the lesser bond angle than that, then the ring strain is getting developed in those compounds. So here, if you talk about the 5-membered ring, the ring strain is only 1 degree. So that is why it is free from this ring strain, although 6-membered ring also having the ring strain, because it is going away from the 109-degree angle. So 5-membered ring is in turn more stable than 6-membered ring if you talk about the ring strain. So is it clear to all of you this much? Any questions in this?
No, no.
Okay, so there are two concepts which you have to learn, that the ring strain is due to the Bayer strain theory, and second is because of the torsional strain which is present between the eclipsing hydrogens which are present on this cyclopropane ring. They are eclipsing to each other. They are eclipsed conformations. So that is why there is a torsional strain. So now, coming back to the question, so they want us to identify the compound with the highest ring strain. So the option B is the correct answer. Agreed with me? Any other opinion than that? Okay. So, should I proceed to problem number 13?
Yes, ma'am.
Coming to the problem number 13. So, they are asking, conformations are the different arrangement of atom that can be converted into one another by rotation about which bond? Is it a covalent bond?
Covalent bond.
Sorry?
Single bond.
Single bond. Yeah, very straightforward question. So conformations can only arise when you have a single bond, because double bond rotation is not possible, and also the triple bond rotation is not possible. So conformations are the different arrangement. You are not breaking the bonds, right? So the main difference which you need to know between the configuration and the conformation is, in the configuration you need to break the bond, but in conformation this is the rotated structures only. You are not breaking any covalent bond. You are just rotating the bonds. So you are not breaking any bond. Okay, so in configuration you are breaking the bond and then you are making another configuration. But conformations are solely dependent upon the rotations of the compound around the single bond. So here the correct answer should be option number C, single bond.
Ma'am, covalent bond.
Yeah, you can say that, but the main feature of that thing is you must have to have that single bond here. Okay, sometimes the covalent bond is very much strong, na, it won't rotate. It doesn't depend on the covalency, right? It depends the single bond and rotation. So that is why we are talking about the conformations around the single bond only. So if you have a competition between these things, you will always mark the single bond. Okay.
Okay, ma'am.
So coming to the problem number 14. 13 was a very straightforward question. So guys, in this we are talking about the conformation of cyclohexane, about the boat conformation. So they are asking, in the boat conformation of cyclohexane, the flag pole hydrogens are located at. So the options are on the same carbon, on the adjacent carbon, on C1 and C3, or on C1 and C4. So which are
On
the,
C1 and
sorry,
on C1 and C4.
C4. Any other answer than that? The flag pole.
C1 and C3.
C1 and
C1 and C3.
3. Okay. You are claiming that option C is correct. Okay. Any other answer? See, first of all, you need to know what is the boat conformation, right? So this is the boat conformation of cyclohexane. So now they are talking about the flag pole interactions. So the flag pole interactions is occurring between the hydrogens of this boat conformation. So these two hydrogen, also there is also a hydrogen, right? I'm not writing it, but please, carbon has 4 valency. Okay. So these are also the hydrogen which is present here. So it is the boat conformation. Now they are asking the flagpole hydrogens are located at. See here, in the boat conformation, there is torsional strain which is present between these hydrogens. So here the flagpole hydrogen, they are talking about the flagpole hydrogens. There is a name which is giving to these hydrogens, dedicated to these hydrogens, that is the flagpole. So there are flagpole interaction which is occurring at the C1, as you can name it, C1 and C4. Okay, so it is not C1 and C3, it is between the C1 and C4 the flagpole interactions are there. So here hydrogens are trying to occupy some same space, unfavorable steric strain is there. So that is why the flagpole interactions and the flagpole hydrogens are located at C1 and C4. So you need to know the boat structure, boat conformation structure, and also the hydrogens which are coming together. Here there are two hydrogens which are coming in the proximity. So here they are named it as flagpole hydrogens. So the location is at C1 and at C4. Okay. Any doubts on this? Correct answer should be,
C1 and C4.
yeah, C1 and C4. So as you can see here, if you number these carbons, then you will see that C1 and C4 have the hydrogens which is having the flagpole interaction. So this is the unfavorable steric interactions only. Okay, because the two hydrogens are coming in the close proximity. So this is the flagpole interaction. This is a very common interaction, and this is the name which is dedicated to this particular interaction. Fine. So is it understood to everyone? Okay.
Yes, ma'am.
I'm coming to problem number 15. So it is also a very straightforward question. So how many isomer does C16H14 have? C16H14 means hexane, right? So how many isomer does hexane molecule have? Can anyone tell me how many isomers does it have? And you have to name it, right? So better write it. So how many isomers can you find about for the hexane molecule? Anyone? I thought it is a simple question, guys. Hexane molecule isomer you have to find. What is hexane? This is hexane molecule. These are the two methyl groups which is present here. This is also a methyl group. So how many isomer does it have?
4.
4. Okay, so you guys have responded. Thank God. Okay, any other answer than 4?
3, ma'am.
3. Okay. Any other answer than this? Is it 3 or 4? 3 and 4. I'm not able to understand what is happening here. If someone wants to join, or why I'm getting a notification? Okay. So coming back to the question, here they are asking about the hexane isomers. So guys, this is the answer. Here you have to place these methyls according to this. So first of all, hexane is a linear molecule. So now there could be 2 methyl pentane. It could have a 3 methyl. Once you can place this particular ring, in this particular ring chain, you can place methyls in different fashion. So if it is this is 5, this is 6. So here you can place one methyl at this C2 position, one at C3 position. So that is why you are getting 2 methyl pentane and 3 methyl pentane. Okay. You can also place these two methyl at a same position. You can also place at the adjacent positions. So that is why you are getting 2,2-dimethyl butane and 2,3-dimethyl butane. So this is how you can play with the methyl which is present in this group. Play with the carbons actually. So there are 4 isomers which could be possible for the hexane molecule. So it is hexane, uh, basically 2-methyl pentane, 3-methyl pentane, 2,2-dimethyl butane, and 2,3-dimethyl butane. So other than these 4, you cannot have any other isomer for hexane. So those who are telling the 3, you must be missing one of the isomer. Is it understood to all of you why it is having 4 isomers, not 3? Yeah.
Okay. Ma'am,
Yeah.
when we are considering this isomer question, so we should consider N or not. When this question is asked, we should consider N isomer or not.
Actually, they in the question they are given the hexane, na? So it is the n hexane. No, you don't have to count the n hexane. If they are saying calculate the isomer for all the isomers for the hexane, actually hexane is basically n hexane, na? So it is not an isomer. It is not isomerizing or something. It's a linear chain. So you cannot count it as a isomer either. Okay, so the isomers are the arrangement, different arrangement of the groups, which is present in the linear chain. So
So
hexane,
if such a
yeah,
question is asked at that time, we should not consider N isomer, right?
yeah, an isomer is not considered. It is only the 4 isomer which could be formed by this butane. Okay.
Ma'am, it has also have 3,3-dimethyl butane, ma'am.
3,3 dimethyl.
Butane.
Okay, 3,3 dimethyl butane. Okay, so you are considering here 3,3 dimethyl butane. So just tell me, if I just switch these carbons, these methyl group to this position. Fine. This is what you are saying, na? Instead of getting
Yes, ma'am.
2,2 dimethyl, I am getting 3,3 dimethyl. But now number it once. 1, 2, 3, and 4. Fine. This is how you are going to number it according to the IUPAC rule. Two methyls are
Yes,
getting the higher preference, so we are starting this at this position because there is no other substituent to be biased. So here you are getting 1, 2. So at 2 position again you are getting 2,2 dimethyl. So it is not possible to have 3,3 dimethyl until you have other substituent which is present. Okay. So if you draw this conformation according to this, you will end up having same identical molecule, na? So that is why it is not the 3,3 dimethyl butane. Is it
yes,
understood?
ma'am.
Got your answer right?
Yes, ma'am.
Okay. So these are the
Cyclic isomer are also there.
sorry.
Cyclic isomer. It has cyclobutane.
It has a
There may be. It has cyclobutane.
it has cyclobutane. I'm not understanding actually. What are you saying?
In it, actually, hydrogen atoms won't comply with it. Substituted cyclobutane, hydrogen atoms won't comply actually.
Hmm. So in cyclobutanes there is another there is restrictions actually. So you cannot which you can do with this, you cannot do with this system, right? It is a cyclic system.
No, no, madam. Cyclobutane, there is derivative of cyclobutane. The ethyl group is influence of hydrogen.
Actually, I'm not getting your question. What you are asking about the cyclobutane moiety?
The derivative of cyclobutane.
Hmm.
What
The ethyl
derivative you are saying? No,
then is ethyl.
Just
in that
One ethyl group
hydrogens
is
will
replaced.
be H10 only. In that hydrogens will be H10 only. They won't comply with the molecular formula.
can anyone tell me the question, please?
He is saying that if we are comparing with butyl cyclobutane and substituted cyclobutane is there.
Okay.
So in that case, if substituted one will be there, right? So in that case, this cyclobutane we can substitute with ethyl group.
Okay. Ethyl group.
So yeah, it won't be this. Will it come as an this isomer of the cyclohexane?
No, no, it is not coming to the cyclohexane isomer.
Sorry, isomer of the hexane. Sorry.
Isomer of the hexane. Is it correct, right? He's asking that if you write it as a substituted butane, which is ethyl substitution, so it is the isomer of cyclohexane or not. He's asking that, right?
Isomer of hexane. Sorry, ma'am.
Hexane, okay, okay, hexane isomer. No, it can't be, na? How it come the isomer of cyclohexane? Sorry, hexane.
That only. Hydrogens won't comply. Number of
Yeah.
hydrogens won't comply.
Yes. The hydrogen is not which is present in this hexane system, na? So that is why it is not a isomer of this hexane system. Because here when you see
Okay,
number of
that
hydrogens
is
are
not okay.
less, right? Okay. Have you understood?
Yes, ma'am.
Okay. Thank you so much, guys. Sorry for not understanding because it is not that much audible level. Okay, so the answer for this particular question is C6H14 having the isomers that is 4. The right answer is 4. Okay, I hope all of you have got the answer why it is 4. So coming to problem number 16. So now there are 4 questions in this particular problem, guys. So what they are asking is determine if the cis or trans chair conformation is more stable for each of the following molecules. So first of all, you need to draw the cis and trans chair conformation for all the 4. So taking first part, 1,2 cyclohexane. So now you have to draw both cis and trans conformation of this particular moiety. So what happens here is I am talking about this system only. First question. We will slowly go through all the 4. Okay. So what they are telling is determine the more stable conformation. So first of all, you need to write the cis and trans conformation. So this is the trans conformation for 1,2-dibromocyclohexane, and this is the cis conformation for 1,2-dibromocyclohexane. Is it right for everyone who understand what is cis and what is trans? Anyone has any doubt in cis and trans, how they are drawing it? Okay, no. So now you have to compare the stability. So can anyone tell me which is more stable among these two?
Trans.
Trans. Anyone with having cis? Anyone saying cis? You guys are intelligent then. Okay, why trans?
The distance between both of the atoms will be more, so steric strain will be less.
Yeah, steric you can say, but here the steric will come into picture if the Br is present at eclipse position, guys. Fine. So there is a better position for this particular conformation to attain, that is this. If you draw it like this is also trans conformation, one is below, one is above, but it can be relieved if you draw if we draw it like this. So here there is no steric strain in the trans conformation. So the main reason which is here is both the Br in the trans having the axial substituent. Okay, but here in the cis conformation you can see that one of the Br is setting at equatorial, so particularly preference is given to equatorial positions. Okay, but in this case conceptually the trans is more stable than cis. Why? Because here if you see this is a polar bond, Cbr bond is polar because Br is electronegative atom, right? So here if you say the dipole moment which is present here, the net dipole moment in both the cases which is pointing towards the more electronegative atom, now they are cancelling each other, so the dipole moment which is present in this system is 0. The dipole moment which is present in this system is 0, equal to 0, because both the Br is contributing similarly, and here the Cbr bond is polarized, it is long. Now the dipole moment is getting generated, and the dipole moment plays an important role in the stability of this trans conformation rather than the cis conformation, because in cis as you can see the dipole is not cancelled by each other, but here it is cancelling. So now preference for equatorial position of the Br is now competing with the this dipole moment. So here if you are saying that one of the Br in the cis is coming at the equatorial, which is governing the stability consequences. But you also need to know that both the Br having the same electronegativity, same dipole moment, same polarization, it is cancelling each other. That is why it is uh, setting the conformation to a higher level of stability than the cis conformation. Is it clear to everyone that why trans is more stable than cis. Although cis has one of the bromine atom present at the equatorial, whereas trans has both the Br atom present at the axial position.
Ma'am, in case of second condition, what you have said,
Yeah.
so we are both are in the equatorial position.
Huh.
So, but in that case, one is above the plane, one is below the plane, right? So that condition will also become a trans only, right?
Yeah, that will come a trans only. But as I've told you, that one conformation can also have other set of conformation, as we have seen in this particular case. One of the case was there, right? Yeah. This is the example of this particular situation. Here also you have seen that both the A and C, both conformations are possible for this particular system. Both conformations are totally satisfying the stereochemistry as well as the sterics for equatorial, right? But here you choose option number A. Why? Because here the steric strains are there between the methyl group, right? So because of the steric strain, system chooses a favored conformation rather than the C. Understanding my concern?
Yes, ma'am.
Yeah.
Yes, ma'am.
So
Got it.
similarly, on the same line, we have to set the equation like this only, that the compound will favor the conformation which is more stable, right? So that is why it is also trans, but compound will go for this conformation rather than this. Okay. So that is why we are
Okay.
drawing a more stable conformation. Whenever you are drawing a conformation, please draw the stable conformation for the comparison. Okay. So here, up to this is clear, or anyone has any question, please feel free to ask. Any questions, guys, in this particular part one? Okay, there is no question. So, this is the more stable conformation, that is the trans one for this 1,2-dibromo cyclohexane. Okay. So now coming to part B. Now they are telling about 1,3. This should be dimethyl. Okay. This should be dimethyl. 1,3-dimethyl cyclohexane. So now 1,3-dimethyl cyclohexane. Coming to this. This is the part 2. So I have drawn already the cis and trans conformation for both the 1,3-dimethyl cyclohexane. So now can anyone tell me which is the stable conformation?
Trans.
Trans. Anyone for cis? Anyone for cis conformation?
Trans.
Okay. Okay. So here it is a very straightforward thing that all two methyls are there, so they will prefer equatorial position. So there is no other factor which is governing the stability. So now the trans conformation for this 1,3-dimethyl cyclohexane, it is more stable, right? Clear to everyone? I hope it is clear to everyone.
Yes, ma'am.
Yeah.
If there's an equatorial, if it's in the equatorial position, it is more stable.
Yeah.
If any one of them is.
Yeah. Yeah, any one of methyl group. If you don't have, see, if you don't have any other choice, see, in 1,3-dimethyl cyclohexane, you don't have any other choice. One substituent has to have on the axial position. Okay, if you draw the trans conformation, one substituent should be at axial position in this particular set of stereochemistry. So here the trans conformation is the conformation which is more stable than the cis conformation, because in cis both the methyl are axial composition, and here the 1,3 diaxial interaction is facing by these two methyl groups. But here only one methyl group is facing the 1,3 diaxial interaction, so which in turn thermodynamically it is more stable than this cis conformation. Is it understood now?
Yes, ma'am.
So now coming to problem number C. So here part number C, they are telling about 1,4-dimethyl cyclohexane. So this is the part number 3, 1,4-dimethyl cyclohexane. So I have drawn both the cis and trans conformation, guys. Which is stable? Very straightforward. Which is stable, guys?
Ma'am, both are the trans only, right?
Yeah, both are the trans only. So it reflects that all of you are thinking, right? So that's why it is a on purpose I have put it like this. So you can draw the cis conformation by your own. So guys, what happens here? Both the methyl, if you draw the cis conformation, both the methyl should be above the plane, right? So both will go at axial position. One axial and one equatorial will be there, right? If you draw it as like, if this is above the plane, methyl, I'm drawing it like this. If you compare this, it is a cis isomer and it is a trans isomer, right? So in cis isomer, one of the methyl group is present at axial position, and at trans isomer you have both the methyl which could be at equatorial position. So which one will be preferable? Which one will be more stable? The trans one, because in this case both the methyl can have the equatorial positions, right? But in the axial, if you taken up the cis conformation, one axial methyl should be there. So here you can see that the trans conformation is preferred. Is it clear to everyone? Okay.
Ma'am, in second question, if both of them are in the equatorial position,
Hmm.
in the case of cis, will there be stable? Will they be stable?
If both of them can be at equatorial position, right?
Yeah, both are in the equatorial position. They will be cis, right?
They will be cis. Yeah.
So they will be stable.
Yeah, they will be stable. If you have to draw it, see 1,3 dimethyl now. So if you have to draw it like this, if you are drawing it here, so the cis conformation has both the above the plane. So try drawing it. I will prefer try drawing it, because if you have 1,3 set now, then 1, 2, 3. Either way, if you are going through, if you draw this methyl here, then only you will have this 2-methyl up and or 2-methyl down. Both will be cis, right? If you have 2-methyl at the equatorial position, then it will be stable.
So it will be more stable than the trans.
Yeah, it will be more stable than the trans. What you have need to know is the stereochemistry, correct, and what you need to know the sterics. That's all. Okay.
Okay.
Okay. Now coming to the part 4, that is the 2-bromo 1-iodocyclohexane. So 1-bromo 2-iodocyclohexane. So these are the cis and trans structure for this 1-bromo 2-iodocyclohexane. This is the trans form, similar on this line, and this is the cis form. So which would be more stable according to you guys?
Trans.
Trans. Someone with cis. See, you need to apply the concept of electronegativity, and which in turn is playing the role in the dipole moment, right? So here it is not similar than one, because here what happens is you both the substituents are different. So now you have to know that the electronegativity values of Br and iodine is not similar, right? Iodide and bromide have different electronegativity, right? So the electronegativity is not same. So now here, if the CBr bond is more polarized, the Ci bond is not that much polarized. So the dipole moment which is getting generated here uh, is not equal, right or not? Getting my point why the electronegativity is playing a role in this particular concept?
Yes, ma'am.
Yeah. So here what comes into picture is the atomic radius. So if you have a particular substituent which can have a axial position freely, you will have that conformation as the more stable conformation. See, what you need to know is we want the substituent to be at equatorial position anyhow. Okay, here, this is stable because of the dipole moment it is getting cancelled. So that is why it is getting a stable conformation. But here, the electronegativity of bromine and the iodine is very different. So that is why you are not getting the dipole moment values equal. So here, you want both the atom to occupy the equatorial position for the stability. But now what happens here is in the you have both the atoms at the axial position. But if you go to the cis conformation, you have one of the atom at equatorial position. So one way of drawing it is as if I draw this chair conformation like this, and if I have this iodine, this Br in the place of iodine. Just imagine if there is a scenario, this Br is here and iodine, this iodide atom is here, right, at the equatorial position. So if I say that you have to compare in between these two, which will be more stable? Any guesses?
Iodine at the equatorial.
Iodine at the equatorial. Any other answer? Anyone supporting Br at equatorial? Okay. So guys, what I have told you is the atomic radius, right? More the atomic radius, see the polarization is also there, some polarization is also there, na? But the atomic radius of this iodine is such that it is it is the longer bond. Ci bond is the longer bond because of the atomic radius of this iodine, right? We have studied this. The Cbr bond is shorter than Ci because iodine is having the higher atomic radius. So the longer the bond, so here the 1,3 diagonal interaction which is facing by these hydrogens is less, because now the iodine is not very much closer to these hydrogens. So if you have to compare between iodine at equatorial or bromide at equatorial, oh sorry, iodide at axial or bromide at axial. So if you have to compare two situations, you will also always prefer that iodine will occupy the axial position because of the longer bond length. If the bond length increases, then iodine is not in the close proximity of these methyl to get the 1,3 diaxial interaction very strong. But if Br is placed at this position of the iodide, here the 1,3 diaxial interaction is more because Cbr bond is not that much long. Although it is polar, but it's not longer than Ci bond because of the atomic radius. So now you have to see all the aspects of the following substituent, what it can impart, electronegativity, atomic radius, or the A values. So you have to see that also. So here the more stable conformation will be this conformation where the iodide is present at the axial substituent.
But ma'am,
Yeah.
in case of equatorial position, if longer bond length is there, then interaction between carbon atom and iodine will be reduced when we are comparing carbon and bromine, right? So why we can't consider the equatorial position?
See, here, if you are confusing with these two conformers, see what happens here is I am telling that if the see, all the substituents want to be at equatorial, right? So this is the
Yes.
primary rule which we are studying here. The equatorial has less energy than the axial, right? But what happens here is in the cis conformation, one of the substituent is going at the equatorial, but one other substituent is at axial. So now you have to compete the two substituents which will be placed at axial or which will be placed at equatorial. So if I place iodide as an axial substituent. What happens that Ci bond length is greater than Cbr bond length. So that is why iodide is not facing that much 1,3 diaxial interaction strain, which Br is facing in this particular situation. So Br will face 1,3 diaxial interaction more than Ci bond, iodide basically. So that is why it is going to axial. If you have to have one group at axial, in this case, Br will not go at axial. It will prefer equatorial because Ci bond is longer and iodide has a higher atomic radius. It will shorten, it will lessen the 1,3 diaxial interaction in this particular case, right? But here Br is facing higher 1,3 diagonal interaction. That is why this particular conformer is not that much stable. Is it clear now?
Not that much, ma'am, because in case of equatorial also the same phenomena we can apply,
In the case of
right?
equatorial, what you are placing at equatorial? Which group you are placing?
Iodine.
Okay, this you are talking about this particular system, right? This particular.
Yeah. So in that case, hydrogens means what you are saying is that Br is having more influence, or by Br is having more choices than the iodine. Is that correct?
We are having the more choice and according to the atomic radius I am talking about. Okay. And what is your question then? Continue.
If we are considering iodine at the equatorial position,
Right.
so all the same thing is happening, because equatorial hydrogens are going to have less interactions when we are comparing with the iodine.
Yeah. This
So
hydrogen you are talking about, right?
yes, yes.
Yeah.
So is it? So it is also preferable, right? So what I'm confusing about is that iodine and bromine is there. So in that case, bromine is getting more choice than the iodine when we are comparing with the substitution.
No, it's not like that. See, what you are saying now, I understood. Here you are saying that these hydrogens are, because iodine is longer, now these hydrogens are not facing that much steric hindrance. So it is also a positive point of having this iodine at this equatorial position, right? But what
Yes.
happens here is, see, iodine having the higher atomic radius, right? So as I have told you, hydrogen bulkiness is increasing. This is governed by steric hindrance, right? So here bulkiness is increased because of iodide group. Br is smaller than iodine. I am talking about the axial bond length. It is getting increased so that the 1,4 diaxial interaction is not coming into the play in the picture that much. But here the interaction is there, right? Interaction is there in both the cases. Here also, if you are saying about these hydrogen which are present at the equatorial position, just tell me the steric hindrance is more in C in HBr, or the steric hindrance is more in H and I. Which is more bulky, iodide or the bromide?
Obviously, iodide is more
Obviously,
bulky.
iodide is more bulky. So here the steric strain is more in this case. So it is not getting an advantage. See, the equatorial bond cannot be stretched too much than the hydrogen is getting. I am just saying that this bond is longer, so that this is getting weaker. This interaction, because hydrogens are far apart, but here the hydrogen is not far apart. It is present directly towards the iodide, right? In both the
Okay.
cases. Here
Yeah,
it
got
is
it.
far apart, 1 and 3. It is not adjacent to the carbon, right? So here you
Okay.
have no more space to go unless you are having a steric strain. You are having a more steric strain in this Ci than the this H and Br, right? So here it
Yes,
is
ma'am.
also decreasing the probability of this conformation to be in this conformation. So here it is not a positive point, it is a negative only, because the 1,3 action interaction can be relieved some way, but the steric of the adjacent carbon of the equatorial positions cannot be relaxed in any way. Okay?
Yes, yes, got it, ma'am. Thank you.
Yeah, okay. So I hope all of you have got this answer. So here the more stable conformation is this. this is the more stable conformation. Here the this is the more stable conformation. Okay, and these are the very basic questions. So you have got how these particular conformations are less stable or more stable. So I hope all of these four parts are like clear to all of you. If you have any problem, just ask me. So shall I proceed to problem number 17?
Yes.
Yes, ma'am.
Okay. So now comes the main questions of nomenclature of the bicyclic compound. So most of you know this concept, most of you doesn't. So for the people who doesn't know, please understand this concept because it is bit tricky, but it is very straightforward. So here what they are telling is name the following bicyclic compound. See, you have named various compound according to the IUPAC, but the bicyclic compound nomenclature is somewhat different from the cyclic compounds. So here from the linear compounds. Sorry. So the bicyclic compounds you have to name. So anyone knows how to name these kind of compounds so that the former ones can get the answer.
Is it bicyclo 331 cyclonone?
This bicyclo 331 cyclonone. Okay. So what she is claiming, let's see this is correct or not. Okay. So here, first of all, the criteria of the nomenclature of this bicyclic compound is like that. First of all, you need to know that you have to use the term bicyclo. Okay, and then the parent chain you have to calculate. The number of carbon present in all the rings. So if you are calling it as here, this is the one ring, this is the first ring, this is the another ring, and this is another ring, right? So there are three rings. So now you have to arrange that ring and the carbon numbers according to the preferences. So here, first of all, you have to you have to write the ring having the highest number of carbons. Then the series will continue. First of all, if this ring has the 4 carbon, then you will write as 4 3 1. So you have to number according to the number of carbon that are present in the ring. So highest number of the carbons will get the preference first of all. So you need to write bicyclo, then the number of carbon corresponding in each of the ring, and then the parent chain. Parent chain meaning like the number of total number of carbon that are present in the compound. This is the parent chain. So if you calculate the total number of carbon which is present here is, if you number it like 1, 2, 3, 4, 5, 6, 7, 8, and 1 9 at the bridging. This is the 9 carbon. So total number of carbons are 9. So it is a no-name structure, right? That, like you have told, like hexane, heptane, octane, no-name. So you have to write in that order. So the parent chain is the total number of carbon atoms that are present in the ring, and the bicyclic is the nomenclature you used first of all to write the bicyclic compound nomenclature. So now, if you need to write the name of this compound, you first need to write bicyclo, then you need to write the number of carbon in each ring. So how many rings are there? Three rings are there. I have told you this is a ring, another ring is this, and another ring is this. So there are total three rings which is present in this particular system, right? So you have to write first of all the bicyclo. This is the nomenclature. This is the general nomenclature scheme which we are using in nomenclature of these kind of compound. So you have to first write bicyclo, then you have to number the carbons which is present in each rings. So now 1, 2, and 3. So this ring has 3 carbons. Now this ring, if you take this ring, middle ring, then you have only 1 carbon which is present. Irrespective of this fused carbon, this is irrespective of this common carbon, you have to count all the other carbons, right? Don't count these carbon because it is present in each of the ring. It is common for each of the ring. Okay, so that is why don't count this bridgehead carbons. So here, first ring has three carbon atoms. If you talk about this ring, it has only one carbon atom. If you talk about this ring, it has also three carbon atom, right? Three carbon atoms are there. So now I have told you, you have to arrange these three numbers according to higher to lower. So here you will write 3 dot 3 again, because you are numbering it like 1 3 3 and the lowest number now, which is 1. So this is 3 3 1 system. 3 3 1. So you need to write the bicyclo 3 3 1 and total number of carbon atom, that is the parent chain, which is no name. So here comes the name bicyclo 3 3, no name. So is it clear to all of you how we are going to number these kind of compounds? Any questions up to here?
Yes, ma'am.
Okay. So if I would place a substituent on this ring, then you have to write the substituent name first and then you need to write this bicyclo 3 3 1, right? So now we will see how it is work. So see, in the problem number 18, I hope all of you have understood the nomenclature scheme. The general one I have placed, and now the one with substitution. So now you have to name the compound. So here also what you need to know is the I have told you that you first have to number with that ring which has higher number of carbon. So there is a competition here between this ring and this ring, because in this ring you have 1 2 and in this ring you have 1 2 and 3 carbon atom. Is it visible to everyone how I am seeing the carbon atoms? You can see,
Yes, ma'am.
no? You can
Yes.
see, you can relate, right? Okay. So here, what you have to write is, according to this, you have to write this. So this is the particular rule that the largest string is numbered first, regardless of the substituent. So the largest string you have to number first. So this 1, 2, 3, 4, 5, and 6. So in this way, you have to number the largest number. The largest number of carbon atom ring will have the highest preference, irrespective of the substituent which in which ring it is placed. Okay. So here, this kind of numbering you have done. Now bromo is arriving at 5 positions. So first of all, you need to write the bromo. First of all, you need to write the substituent. So it is 5 bromo. Yeah.
Ma'am, it will
Between 3 and 4, another carbon is there. Between 3 and 4.
Oh, sorry. I missed one carbon. Thank you so much. I missed one carbon. Sorry. Mistake. Sorry, guys. So here it is 6. I missed one carbon. So all of you are attentive. Very good. Nice. So it would be 6. It would be 6 bromo. Fine. It would be 6 bromo, and then the naming will start. The bicyclo and the ring number of carbon atom and the parent chain. So now the parent chain is 1 2 3 4 5 6 7 and 8. So it is an octane system. Fine. So now you can see that 6 bromo bicyclo. First of all, you have to write the highest number, that is 1 2 3 3. Second ring having the 2 number of carbon atom 1 2, and the third ring which is present at this having only one carbon atom. So you need to write 1. Okay. So this is how you are going to nomenclature. You are going to name a bicyclic compound. So first of all, you have to know the largest ring is numbered first, uh, and all the ring atoms, all the carbon atom which is present in each ring, you have to write them in the increasing order. Sorry, decreasing order. So first of all, you have to write the highest number of carbon atom in the ring. Then the other ring is considered which having the lowest lower carbon atom and the lowest carbon atom. Okay. So this is how you are going to name a particular bicyclic compound. Is it clear to all of you till now up to there?
Yes, ma'am.
Any confusion, anything which is not clear up to this question?
It is clear.
Okay. So if it is clear, then I have a question, another question based on this same line. So you have to name this particular system. So if it is clear, the question number 17 and 18, then just tell me what is the name of this compound. Anyone? So from where you will start the numbering? First of all, number it. So the highest ring will get a preference regardless of the substituent. Although this ring has two substituent present, but you will have to number this ring first because it has more number of carbon atoms. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, and clear to everyone how I am going to name this compound, how I have to
Ma'am,
give the numbering.
ma'am,
Yeah.
we can start the numbering from other side also, right?
So you can
By
start
that means we can get the methyl group
methyl at
second
lower.
number.
Yeah, yeah. You can start that thing also. You can do. I'm just
So
giving
both
her
is
this that
correct.
you have to remember that this ring is coming first. Okay, you need to start this numbering from this carbon only because the preference of this methyl will come at 3. Then at this starting you are getting the methyl at 4, but if you start by this you will get a methyl preference at 3. That is why you need to start from this one, but you have to give the number to this ring first of all. Okay, this is what I am implying. Okay, so now if you have arrived to this particular confirmation, now just tell me the name of this compound. Anyone? It is 3. It is actually 8 or what?
3-methyl 7-chloro, 7-chloro 3-methyl 8 dimethyl
Hmm? 3,
4
2,
2
3.
2 bicyclo 4-2-2
Mm-hmm. Decane.
decane.
Yeah. This is 7 chloro 3 8 dimethyl bicyclo 422 decane. Is it understood to everyone? See, first you have to see which is the ring having the highest number of carbon atom. Then you need to see if you are numbering that ring, you will have that substituent with the lower priority, right? You have that particular methyl group at the 3 position rather than the 4 position if you go from this side. So it is also you have to keep in the mind the IUPAC nomenclature rules. You have to keep in mind as well. Okay. So is it clear why this compound is 7-chloro-3-8 dimethyl bicyclo 422 decane? Any questions up to here?
It is clear.
It is clear. Okay. So it is clear for all the things, all the compounds, why and how we are naming these compounds. Clear to everyone? Okay, guys, if it is clear, so I hope it is clear. So this is the last question. So here we are ending the session. So I hope you guys have got all the questions, and if you have any problem regarding any of the question, please feel free to ask in the next session. We will be meeting in the another Saturday, next Saturday, 6 to 8. So hope to see you there. So I hope all of you have got the today's lecture, whatever the tutorial is. So if you have any doubt, please tell me in the comment box. Also, you can post. I will put this video on the YouTube channel, and you will catch this video there. Also, you can see multiple times. And also, if you have any query regarding that, please ask me in the chat box or in the next session whenever you feel comfortable to ask. Okay. So I am closing this session right now. If you have any question, just tell me.
Thank you.